right, let's look at example 5. For example number 5, if we try to evaluate the limit, we're going to have the limit as x approaches infinity of, if we put infinity in here, you're going to have infinity squared. Now, we're not actually saying that infinity is a number that you can square and come up with a numerical value. Infinity is a symbol that represents the concept of something getting infinitely larger without bound. But if you take something getting infinitely larger without bound and multiply it times something getting infinitely larger without bound, you get something getting infinitely larger without bound. And then if you add 1 to that, it's still getting infinitely larger without bound. And if you take the square root of that, it's still getting infinitely larger without bound. So although it would be a little slower, this would give you a value of infinity. And when I plug infinity in here, same idea. We're going to end up with infinity minus infinity over 1. Now again, we're not actually regarding infinity as a number that can be added or subtracted or multiplied anywhere in this lesson. But rather than write out a 4-sentence explanation of a quantity getting infinitely larger without bound times itself plus 1 square root of that minus a quantity getting infinitely larger without bound is still going. Rather than write it that way, we are going to use the symbolism of infinity minus infinity. However, on the AP exam, we would never write anything like that in the FRQs that would lead them to think that we were regarding infinity as a numerical value. We know that it's the symbol that represents a quantity getting infinitely larger without bound. But we do need something when we're working out 15 homework problems to, keep track of our idea of where this problem is going. So we've got infinity minus infinity over 1. I don't have any way of determining what that is. That could be 0. It could be one getting infinitely larger faster than the other, so it could be infinity or negative. There's just no way to determine that. It's actually an indeterminate form, and we're going to use some of the things that we've already learned about limits to help us figure these problems out, and then later on we'll also get some additional tools that we can use to help us with indeterminate forms. But one of the things that we had learned previously was to divide everything by the highest power of x in the denominator. I don't have an x in the denominator, so I can't do that. We've also learned to compare the degree of the numerator with the degree of the denominator. So the degree of the numerator, square root of x squared, is x to the first. The degree of the denominator is x to the 0. So I know since the degree of the numerator is larger than the degree of the denominator, I'm not going to get a horizontal asymptote, which means I'm not going to get a limit. So I'm going to end up with some type of a limit that doesn't exist, whether it's infinity or negative infinity or something along those lines. So algebraically, something that we had done in the past was to multiply by the conjugate when what we had was not able to be determined. In a conjugate, remember, you're going to use the exact same first term, the exact same second term, but the opposite sign in between. So same first term, same second term, opposite sign in between. I don't change this sign. And of course, what I do to the numerator, I also do to the denominator. So let's FOIL that out. So we'll have the square root times the square root would be equal to that quantity squared. So that's where we get the x squared plus 1. And then the square root times a positive x and the square root times a negative x drop each other out. Negative x times positive x is negative x squared. And in our denominator, 1 times that conjugate is just going to give us the conjugate. Our x squareds cancel in the numerator, and so that leaves us with 1 in the numerator. In our denominator, we've already talked about this idea of infinity squared plus 1, the square root of that, would still be infinity, a quantity getting infinitely larger without bound, plus a quantity getting infinitely larger without bound. So if you take something getting infinitely larger without bound plus something getting infinitely larger without bound, you get something getting infinitely larger without bound. So if my numerator is staying the same and my denominator is getting larger and larger, my overall fraction is going to get smaller and smaller, and so that limit is going to go to 0. All right, look at example 6. For example 6, I could use logic to figure this out. If I go through and I think about as x approaches infinity, when my numerator is staying the same and my denominator is getting infinitely larger, then that fraction gets smaller and smaller, so that would be like the sine of 0, and I know the sine of 0 is 0. But if I wanted an algebraic way of figuring that out, since it's the 1 over x that's causing us grief here, let's substitute that out. So if I'm going to replace this x with a t, I'm also going to have to replace this x with a t. So I'm going to say, okay, let's replace 1 over x with t. So t is 1 over x, so that gives me sine t. As x is approaching infinity, what is t approaching? So I can come over here and say as x approaches infinity, put infinity in the place of that x. Numerator staying the same, denominator getting infinitely larger without bound, so the overall fraction will get smaller and smaller, so t would go to 0. So as x approaches infinity, t is going to be approaching 0. So now I have something that's well behaved. I can just use direct substitution, and of course we know the sign at 0 is 0. All right, look at example 7. Example 7, we've got the limit as x approaches infinity of sine x. If you think about what the sine curve looks like, here's our sine curve, and as x is going to infinity, as x gets larger and larger and larger, what one value is that limit coming to? Well, it's not. It's constantly going back and forth, positive 1, 0, negative 1, 0, positive 1, 0, negative 1. It's not settling on any one particular value. And so for that reason, we're going to say that this limit does not exist, because you might remember anytime we had a limit that did not converge on one particular value, then that limit did not exist. Another way that we can get a limit that does not exist is if we have a limit of infinity. So if you're taking a limit as you approach infinity and you get an answer of infinity, that's called an infinite limit at infinity. And that's what we see in example number 8. In example number 8, we've got the limit as x approaches infinity of x cubed. So that would be like infinity cubed. Something getting infinitely larger without bounds times something getting infinitely larger without bound times something getting infinitely larger without bound is, of course, going to get infinitely larger without bound very quickly. And so that would give us infinity. And sure enough, if you think about what the graph of y equals x cubed looks like, as x goes to positive infinity, absolutely this function is going to positive infinity. If instead we took the limit as x approaches a negative infinity, then that would be, again, infinity times infinity times infinity is going to give me infinity, and a negative cubed is going to give me negative infinity. The fact that this answer is negative is not because I was approaching negative infinity. If this had been the limit of x to the 4th, then this would have been a positive infinity, because infinity to the 4th is going to be infinity, but a negative to the 4th is going to be positive. So I do have to consider the sign and the value. But in this case, again, if I'm thinking of x cubed, a negative cubed is negative, and so that's why our answer was negative here. And sure enough, if we think about the graph, as x goes to negative infinity, my graph is going to negative infinity as well. All right, look at example 9. Example 9, we have the same problem we did in example 5, in that when we try to plug in, we end up with infinity minus infinity, and that's an indeterminate form. I don't know what to do with that. So I want to see, is there any way that I can simplify it, use anything that we've learned previously? I don't have a fraction, so I can't divide everything by the highest power of x in the denominator. I can't rationalize because I don't have a radical. But something that we had done previously was factor and cancel to simplify. And although I can't cancel, when I factor, it does change this problem. Because if I take out the greatest common factor of x, now when I plug in infinity, now I'm going to get infinity times infinity minus 1, which is infinity. So if I have something getting infinitely larger without bound times something getting infinitely larger without bound, that's going to get infinitely larger without bound. All right, look at example 10. For example 10, we've got the limit as x approaches infinity of x squared plus x over 3 minus x. So since this is rational, I'm going to divide everything by the highest power of x in the denominator. And unlike the first half of this lesson, I end up with an x. In the first half of this lesson, everything that we were left with was a constant or a number divided by a variable, and we had a method for evaluating that, but I'm not really sure what to do with this. So remember, we have those limit laws that tell me if I have the limit of something being added or subtracted or divided, I can break that up into separate limits. So I could take the limit of just the first piece. Since I don't know what that is, I'm going to leave it alone. And then I could take the limit of a constant. We do know that. That's going to be that constant. So notice our limit notation is gone. It's just the limit of that constant is that constant. Then we have the limit of a number divided by a variable. And remember, when we're approaching infinity, the numerator is staying the same. The denominator is getting infinitely larger without bound. So the overall fraction is getting smaller and smaller, going to 0. And that was that property we learned in the first half of the lesson. And then the limit of a constant is that constant. So now I've evaluated every other piece except for this one, and so now I can focus on just that first piece. If I substitute in here, I'm going to get infinity, or something getting infinitely larger without bound, plus 1, so still getting infinitely larger without bound, divided by -1. And so that would give us positive divided by negative is a negative of something getting infinitely larger without bound.